Good evening to one and all present here. Today, I am honored to speak about Dr. Ankita Saini, a beacon of excellence and dedication in the field of chemistry. A gold medalist throughout her academic journey, she completed her PhD at IIT Roorkee, contributing groundbreaking research with far-reaching applications. Her work has been recognized with prestigious awards, including the Young Woman Scientist Award and multiple accolades for a presentation at international conferences. She is a reputed speaker at many national and international conferences where she has shared her expertise and insights with the global scientific community. Dr. Ankita Saini's extensive publications and contributions to scientific literature highlight her role as a leader and innovator. Her dedication to advancing knowledge and fostering education serves as an inspiration to all, demonstrating the power of perseverance and passion in achieving greatness. We welcome you, ma'am.
Thank you so much. Thank you for such a lovely introduction. And heartfelt thanks to Dr. Sarojini ma'am for such a beautiful and heart love and a very hello, hello,
Yes, ma'am, clear, audible, ma'am.
hello. Yeah,
Yes, ma'am. Yes, you
thank
are
you,
audible,
thank you
ma'am.
so much for such. Yeah, thank you so much for such a lovely starter for day two FDP. Shall I start showing the presentation now?
Yes, ma'am, yes.
Okay, okay. Let me know whether it is visible or not, then I will start continuing with it, right?
Yeah.
Yeah.
Visible only, ma'am. Now you are visible.
Okay, okay.
Already you shown. Yes, visible. Slides are visible.
Shall I make it full screen?
Oh, ma'am. Yes, ma'am.
Yes. Okay, okay. Okay, welcome to all the participants on the day two for a 1 week FTP by JIT Chennai on the title of Contemporary Research Trends, Innovation in Materials and Technology. Today, the lecture will be on material science and nanoengineering of organic solar cells. Yesterday on the day one, Dr. Shweta, she told about the nanomaterials and the general basic categories and synthesis of nanomaterials. So in continuation of the day one, today we will be initially looking into the optoelectronics. That will be the I will be briefing about the optoelectronics, what are the need and how they can be related to the material science, and what is the uh, role play of material organic material compounds or material sciences in solar cells application. And then looking into the drawbacks and the benefits of uh, material sciences into solar cells, how the nanotechnology can be incorporated into our photovoltaics, that we will be focusing on today's lecture. Shall I continue, ma'am?
Ma'am. Yes, continue, ma'am.
Okay, thank you so much. Okay, so coming to the introduction part, as we all of us know that energy is the core requirement of our life, and there are various sources of energy which are renewable and non-renewable sources. The renewable sources of energy includes biomass, geothermal, wind energy, or either the hydraulic energy, water energy, and the solar energy. So sun is the supreme source of energy from which we all are dependent for the source of light. So how the technology, engineering, and science can use the light from the sun into the production of electricity. This is the main basic point to be considered here when we look into the photovoltaics application. Okay, so why we need renewable sources of energy? As all of us know that there is an increasing population, and due to the increasing population, we are in requirement for the energy and electricity. So there will be the energy crisis and electricity demand has been increasing. A part of that, there is a lot of degradation to the environment, including the increase in pollution and environmental issues are being raised. So keeping these points into mind, there is a need for renewable source of energy, and here today we'll be talking about the optoelectronics. Yeah, I guess now, okay. So coming to the next slide, what are optoelectronic devices? Optoelectronic devices are the devices which convert the uh, light into the electrical energy, or they produce the electrical energy when incident light fall upon them, or vice versa. So depending on the types of conversion, whether it is from the light to electricity, we can distinguish the optoelectronic cells as solar cells, and if it is from electricity to light, then those will be LEDs, that is the light emitting diodes. So here solar cells, if we look into the solar cells, these dated back to 1950s, and before that into the 1860s, when the photoelectric effect was uh, introduced by Becquerel. So to the next slide, what are the two sources that give rise to the solar cells are? One is the photosynthesis, that is a natural process, and the second one is the photovoltaic effect, or the, we can say, photoelectric effect, which was given in 1839. So in photosynthesis, what happened? The light is converting into the energy, that is the food energy by the green plants, right? And in case of photovoltaic effect or the photoelectric effect, when the light fall on the surface of a metal, the electrons are excited and they leave the surface, leaving behind the charge. Okay, so these two mechanisms, photosynthesis and photoelectric effect, are combined and give rise to the idea for the solar cells. That is the basic construction of the solar cells. So dated back to 1941, when the first silicon solar cell by Russell was introduced. Later, the first efficient silicon solar cell was given in 1954 by Pearson, Fuller, and Chapin. And Tang et al. In 1975 gave the concept of single layer organic solar cell. So here, this is the basic discussion that we are going to discuss in today's talk. Okay, so evolution of the solar cells, as I already told, that the photoelectric effect that was discovered by Becquerel was the main inspiration for the cause of uh, synthesis of the solar cells. Later, the first silicon solar cell by Chapin, which gives the efficiency of 6% in 1954. And decades after, later heterojunction solar cells were introduced, which were the organic solar cells by Tang under the banner of Eastman Kodak, and the solar efficiency is raised to 40.7% in California in the Spectro Lab, which was the totally inorganic solar cell. So a lot of research has been already going on decade back. It is not the the new research area that is introduced in the last one decade only. So they dated back to 1800s and 1900s, but the general exploration in this research area rises from 2010 onwards only, particularly in the organic cell field. Okay, so here all of you can see the classification of various types of photovoltaic cells. So it can be divided into basically three general categories. The first one is the inorganic, the second one is the organic solar cells, and the third one are the hybrids. So depending upon the type of the semiconductor or the type of the PN junction semiconductors being used in the construction of solar cell, these can further be divided into single layer or thin film or hybrid or the multi-junction cell. So in the inorganic photovoltaic cell, PV cell, If the semiconductor being used is silicon semiconductor, and it can be either crystalline or it can be the thin film. So here if you see this silicon semiconductor and the crystalline semiconductor, these are examples of the first generation solar cells, right? Coming to the compound semiconductor, where there were the combination of different copper in so
Ma'am, voice breaks, ma'am. Your voice breaks. Ma'am, voice not clear.
hello,
Yes, ma'am.
hello, yes,
Yes,
am I
yes,
audible?
ma'am. You're audible, ma'am.
Hello,
Yes, audible.
Your voice.
Audible.
actually, hello,
Audible,
did
ma'am.
I miss something?
Audible, ma'am. Ma'am, you are audible.
So coming to the
Audible, ma'am, but voice breaks.
like the P that are the power. These are the example of the third generation solar cells. Okay, so the second generation solar cell belongs to the thin film cells. Now come to the third category, that is the hybrid solar cells. Hybrid solar cells can be divided into a list of categories, but namely I am naming here few only. First one is the dye sensitized, that is the dye sensitized solar cells. Second one is the perovskite solar cells, that is totally inorganic in nature. Third one are the hybrid solar cells, which include the semiconductor plus the nanocrystals. And the fourth one are using the quantum dots, which is the new technology coming on and bringing into the very thin film solar cells. So these are the three basic categories upon which we can rely depending upon the type of the semiconductor or the type of the film that has been formed for the construction of the cell. So the four generations of the solar cell that we can divide upon are the first generation, that is made up of the bulk silicon, but the drawback is they are high cost with high efficiency. The second one is the second generation solar cells. These included the thin film solar cells. It could be amorphous or polycrystalline in nature. And the third one is the third generation solar cells, which comprises of the organic solar cells with the nanocrystalline films. And the fourth generation is the combination of the inorganic nanostructures along with the polymers, or you can say the organic molecules, which give you a flexible layer and a highly low cost cell. So now coming to the basic material science. So material science comprises of various numerous numbers of our pool of functional materials. These functional materials uh, can be inorganic, organic, or it can be polymers. But coming to the organic solar cells, these functional materials are high. Here we will be considering the organic molecules only. And particularly into the optoelectronics, the three types of molecules that are organic in nature and can be used are polymer, oligomers, and the small molecules. So why there is the need for switching into the organic molecules, not into the inorganic substrates? First thing is that comparison to the inorganic, the organic small molecules or the polymers are less toxic. They can be easily functionalized. That is easy tunability is there. It results into low cost and easy processing in the terms of the purification. So organic have a very plus point as compared to the inorganic molecules in the solar cells. So these are the general four reasons why one should go for the organic cells, not for the inorganic ones. Okay, so depending upon the types of the organic cells that I have already told you, let's look into the four categories, basic four examples here, and what are the drawbacks for it that is being compensated into the other category of the uh, photovoltaic. The first one, single layer solar cell. In the single layer solar cell, okay, so before going into it, everyone might be knowing that in a solar cell we have two electrodes. One is anode and cathode, and in between there will be the active material where the exciton will be formed. Exciton is basically a coulombilically bind positive and negative charge, which travels at the interface of p and n junctions, and which then switch into the respective uh, you say homo and lumos of the material being used, and then they transfer to the respective electrodes. So in the single layer solar cell, the two electrodes that are being used are, one is the ITO, that is indium tin oxide, and the second one are the metals. It could be aluminium, calcium, or magnesium in the single layer solar cell. So what is single here? Single means the layer that is sandwiched between the two electrodes is one. That is, the active layer is one only. But what are the drawbacks that come from the single layer solar cell? The drawbacks are, there is a very rapid charge recombination. The charges which are being generated, positive and negative, they recombine and give you the very low efficiency. And the second point is slow charge carrier mobilities. So the charges travel at a very slower rate because the active layer is single, and subsequently it will give the less efficiency. So looking into these three drawbacks, the planar bilayer heterojunction was introduced. In this, what is the difference? We have anode, we have cathode, and in between, instead of the one layer, there are two different layers. One is the p type and the other is the n type. So p type act as donor and the n type act as acceptor. So here the HOMO and LUMOS of both the donor and acceptor will play a very crucial role in the transfer of the electrons, that are the positive and the negative point that are being formed, exciton. uh, these two will be the you say uh, it will be the advantage for this type of heterojunction cell, that the charges will travel more effectively without recombination to the respective electrodes, right? So the recombination factor is somewhat reduced in this when compared to the single layer. But what are the disadvantages further for this type? One is the ineffective exciton diffusion. So diffusion is difficult in this case. Why? Because there is only one layer, one interface is only there, that is between the p and n. So as soon as it reaches the electron and the hole reaches to the respective electrode, they dissociate. So exciton dissociation is the major drawback in this type of case. So to overcome these issue in the exciton diffusion and exciton dissociation, multi-layer solar cell was introduced, where the layer of p and n junction cells are being kept. But the thing here is, this type of cell has a very thick in layer. So this is a very thick cell, and due to the thickness in the cell, the light harvesting is poor, and due to the poor light harvesting, the efficiency of such solar cell diminishes, and there will be the low charge mobilities also, because the charges has to travel from one end to the other end through the multiple interfaces, and the chances for the recombination again increases. So what is the best thing that one can go for? The things that we need to correct here is, first is we have to increase the interfaces. Second, we need to decrease the exciton dissociation before it reaches to the respective electrodes, and we need to increase the efficiency. So this is being overcome by the bulk heterojunction solar cell. So what's the difference between the bulk heterojunction solar cell and the single layer? The difference lies only in the active layer, only in the active layer. Why? Because in the single layer only one type of material is being used as active layer, where both positive and negative charges travel. But in case of the bulk heterojunction, we make a blend of, what do we make? What we make a blend of donor and acceptor, and because of that there are multiple interfaces. Due to the multiple interfaces, the exciton reaches, once it reaches the interface of donor and exciton, it dissociate depending upon the HOMO and the LUMO level. And then now look into the structural design for the organic solar cell. Here we have the glass ITO layer, okay, on which we make a thin film for a whole conducting layer, that is generally a polymer, and it is in a blended form of P dot and PSS, that is the polyethyl deoxythiophene, and PSS is polystyrene sulfonate. So P dot is a whole conducting, that is P type, and PSS is N type, that it mixes with the P dot to enhance the transfer of the charges easily, right? And then we have the two layers, P type positive semiconductor and the N, that will be the N type semiconductor. And in the organic solar cells, what are the P type? P type are generally the donor part. So what is the donor? Donor will be the organic molecule, either it will be a small molecule or it is a polymer. So here in this case we have depicted P3HT, that is poly3-hexyl thiophene, which is a polymer, and it is highly donating in nature, with thiophene is electron donating in nature. And coming to the acceptor part, acceptor is having the electron withdrawing nature, which has a low lying LUMO level. And in general, in the very traditional organic solar cells, if fullerene, that is C60 or C61, they are being used. So PCBM is used as a acceptor here. So if we look into the properties of a donor, so what are the properties of the donor? That the donor should be electron rich in nature, the whole mobility should be high, and it is in the value of 10 raised to power minus 3 centimeter square per volt per second, and it should have a suitable HOMO level, that is highest occupied molecular orbital. It means that HOMO should be in such a way that it has a very low ionization potential. So that means when the light falls on the surface, the electrons are excited from the ground level to the excited level easily. Okay, that means the low ionization potential here. So let's see the value for the HOMO. It is 5.2 electron volt, right? And the LUMO is 3.2 electron volt here. And if we look into the acceptor part, that is the PCBM, so the properties are, it should be electron deficient, have high electron mobility, that is vice versa for the donor part, and it should have deep LUMO level so that it has a high electron affinity. That's why it will extract the electron from the LUMO of the donor to the LUMO of the acceptor. Okay, so if we look into the HOMO and the LUMO level, the HOMO value is 6, that is low lying when compared to HOMO of donor, and the LUMO is 4.2 electron volt, which is lower in energy when compared to the LUMO of the P3HT, right? So these are the basic characteristic before going into the decision that which can act as a donor and which part of a molecule can act as a acceptor. Okay, So the building blocks here, I hope everyone is clear now. One is the organic donor part, that is the whole transporting material. Other one is the organic acceptor part, that is the electron transporting material. The donors can be polymers, these can be small molecules. So here are some of the few examples that acted as donors. And for the acceptors, the generally used are fullerenes and their derivative, or the non-fullerene based acceptors could be used, that are the imides generally, or the polyimides, bisimides or monoimides can be used, or the electron withdrawing groups, that is dicyanovinyl groups, can be used for donors. And further, uh, bifluoride or fluoridine molecules can be used as a acceptor molecules uh, in the organic solar cells. Okay, coming to the next one, this is an animated slide. So let's look into the detail for the working principle of typical organic solar cell. So before going into the animation, I would like to first clear the basic parts. So here we are having the vacuum level 0 electron volt. This is ITO, that is a glass layer. It is a very transparent and polyconducting layer. It do not absorb any light. So that's why indium tin oxide is being used as a general substrate material in case of solar cells. And the value for it below the vacuum is minus 4.7 electron volt. On this, we will make a very thin layer for the uh, uh, whole conducting layer, that is P dot PSS. As I already told about the positive and the negative, uh, this synchronization of both the two polymers, and the value for it will be approximately minus 5.1 electron volt. Then lies the other part of the electrode, that is the metal. Here it is aluminium, and the value you can see is minus 4.3 electron volt. Okay, what is in between the two electrodes? The in between the two electrode is the multi interfaces, right, in the case of bulk heterojunction solar cell. So here we have combination for donor and the acceptor part. So donor have, again, one will be the uh, lower energy level, one is with the higher energy level, that is the HOMO, and the LUMO level, that is highest occupied MO and the lowest unoccupied MO. So what basically is happening, this complete working principle of solar cell, now I'm playing the animation, kindly see. So when the sunlight falls on it, okay, when the sunlight fall on the surface of the metal, the electron from the donor excited, okay, the electron from the donor will excite to the where, okay, so the electron from the donor will jump to the LUMO part here, and because of the low energy gap, the low lying LUMO of the acceptor, this electron will switch to the LUMO of the acceptor part, and then subsequently to the other electrode, depending upon the charges of both the two, right? So here in this case, what are the basic four steps? The four steps, one is the light absorption, when the light falls on the molecule. Okay, second will be the exciton diffusion. The exciton will diffuse, and then will be the charge distribution. The charges will distribute to the respective one, and the charges will be collected at the respective electrode, resulting into the production of the electricity. So how the efficiency, if we say for any device, we look into the efficiency. So how the efficiency of a solar cell is being found? The the answer lies in the solar cell parameters. So here you can see a graph where we have on the x and the y axis current and voltage. So in the dark, the current is zero, right? And when illumination is taking place at 1.5 am, then the short circuit value, the first cut on the I value, that is the current, will be the short circuit current, that is ISC, or we generally represent it as JSC. Okay, you will find this term in the coming slide, JSC. And the second one is the open circuit voltage, that is the VOC. VOC represent open circuit. So these are the two parameters that will give the efficiency of a solar cell. Okay. So the efficiency is basically the what input is being given and what is the output we are getting, right? And it will be like efficiency is equal to JSC into VOC into the fill factor divided by the input value. So what we have given. So what are the basic transition or the processes that we have talked about? So starting from the sunlight, the source from the sun, this coupling of sunlight into the solar cell will take place. It will can result into three phenomena. The first one is the what we are interested in, absorption of the incident photons, right? The other two phenomena that are not the part of the mechanism of solar cell, one is the reflected light and the other one is photons which are not absorbed. So that reduces the efficiency, and this part will be compensated by the nanomaterials. We will look into the coming slides. After the absorption of the incident photons, that is the step one, the excitons will be generated at the interfaces, right, by the electron excitement from the ground level to the excited level from donor part towards the acceptor part, like that. Yeah. So creation of the exciton will take place, and these creation of exciton will then dissociate to give you the free charges, which will travel to give you the current, and these charges will be collected at the respective electrode depending upon the charge. So what is pulling back the solar cell here? The first thing that we looked into, that the light is not completely absorbed, the first drawback. The second drawback is the excitons will recombine again. If exciton is able to give you the free charges, the charges recombine. So these are the general points that are to be uh, keep a check on while introducing the nanoscience into the solar sciences. So molecular engineering is a option to such losses. So what we can do here, we can engineer the band gap of the donor and acceptor. So here what is the aim? The aim is to lower the delta EG, right? So how can the delta EG, that is band gap, what is EG? EG is the band gap between the HOMO of the donor and the LUMO of the acceptor. So this we need to decrease. So how it can be reduced? How it can be reduced? It can be reduced by uplifting the HOMO, and downlifting the LUMO. Simple, right? So by uplifting the HOMO of the donor with respect to HOMO of the acceptor, and how it can be done? By increasing the donor strength. Okay. And how the LUMO can be downlifted? Downlifting LUMO of acceptor with respect to donor while will be by increasing the acceptor strength. Okay. So keeping the VOC max, because JSC and VOC are the core factors that will influence the efficiency. So we need to keep the voltage as a open circuit maximum for this case. Okay. So this I already told that what's pulling us down for the conventional cell. There are main two drawbacks. The first one is the low efficiencies and the second one is the expensive manufacturing cost. So the low efficiency rises from recombination, poor dissociation, or the alternative knockout of an electron from the solar cell principle. And the second reason, that is the expensive manufacturing cost, lies in the silicon and the purification of the silicon, for particularly for the inorganic. So we need to switch to the organic and the polymer solar cells for compensating these two. And when we compare the efficiencies of these type of photovoltaic cell that we have mentioned on this slide, monocrystalline silicon cell, that is the first generation, although the thickness is 0.3 mm, but the efficiency it has given is up to 20%, and which raised to 40% also by the general modification. For the thin film cadmium telluride, the second generation solar cell, 10 to 15 micrometer is the thickness, and however the efficiency lower down and looking into the DSSC and organic photovoltaic for the third generation solar cell, the efficiency has been to the maximum of 25%. But such type of cells are like these are of the standard cells that are in the market. But when we go into the laboratory, the efficiency doesn't give us to the 20% or 25% or 30%. It lies up to 10% only, because we are performing on the very small scale and we are using the lab synthesized organic molecules or donor or the acceptor, and then making a very thin film of the cell and giving us efficiency of 10% or less than that. So the main point here is the thickness is reducing, resulting into the more flexibility of the cell. So why we compare that? Why we are comparing the cells? We are comparing to improve. So where we need to improve is we need to go for the low energy consumption at the fabrication side, because silicon fabrication and its purification cost us the major cost for the solar cell. The second one is for the inexpensive fabrication, and we need more flexible substrates. And as I already told that only like 10% of these has been achieved in the lab. So the issues are to harvest the more photons from the wide range of the spectral sunlight, electromagnetic radiation, and we need to improve the efficiency. We need to develop more good absorption absorbers that also respond to the near UV and to the IR part. And we need to introduce ordered nanostructure, because nanostructure gives us very good properties for charge transfer and separation of the charges in a very uh, useful manner for these optoelectronic cells. So nano engineering is a very is a simple solution to such drawback. So what we need to do, we need to use the ultraviolet light not to be filtered out, it need to be absorbed. And second part is it should be directed towards the interface, resulting into the increased efficiency, and there should not be the recombination part. So that is a main brief out for this slide. So why we need nanomaterials and solar cells? The answer lies in these three main points. First is the efficiency enhancement, and how the efficiency will be enhanced? It will be enhanced by increasing the light trapping. Okay. So, and the second one is enhanced photo carrier collection. Second is physical and chemical properties. As all of us are well known to it, whether it is like at a graduation or the post graduation level, students are being taught nanotechnology. So the physical and chemical properties are known to everyone. It has a very high surface area, and high surface to volume ratio of the nanoparticle give them a very good make them a very good candidate to be used in application. And their electronic and surface properties can be easily modified and changed by the chemical and morphological modification. Third is in improved light trapping. So if that wide range of spectral light can be absorbed easily in form of photons of the sunlight into the exciton, it will definitely result into the higher efficiency, and enhanced electron hole pair creation will be improved. So how these nanoparticles will work in the solar cells? As we know that the nanoparticles, they can be of four types: 0D, 1D, 2D, 3D nanoparticles. So the basic, the one that are being used in the solar optoelectronics are the nanorods, nanowires, or the nanotubes. That are the carbon nanotubes, CNTs we generally call them. So why they are being used? They are being blended with a composite, or they are being replaced by as one of electrode to improve the efficiencies. And how they are being improved? Because they give us a better electron transport property. So electrons are aligned towards them or towards its axis, resulting into the higher capacity for the sunlight absorption. Okay. So size of nanoparticle is a very crucial thing that is to be considered. Smaller the size of the nanoparticle, it will be absorbing towards the lower wavelength, that is towards the blue light, right? So small nanocrystal will absorb the shorter wavelength. So the main thing was shorter wavelength means the band gap EG has been reduced. Okay, that was what our motto, to excite the electrons from the ground of the donor to the lumen with a higher percentage. So nanocrystal will enhance that thing, and changing the shape of the nanocrystal will also change the band gap. As I already told, that the nanorods and nanofibers, or you can say carbon nanotubes, they are being generally used as in case of the combination with the blended form with polymer composites. Okay, so here we have summarized about the advantages of nanostructure layers in the solar cells. The three are being summarized at the bottom of the slide. That first one is, it result into the more absorption, because due to the multiple reflections, the optical path for absorption is much larger than the actual film thickness. Okay, the second is the reduced path. The path has been reduced because they give us the more aligned transfer of the electrons towards the respective electrodes. Third is the tailored band gap. Band gap can be easily tailored by tailoring the size of the nanoparticle by the different use of the synthesis method and methodology. That could be the sol gel method, it could be the chemical vapor deposition, or it could be electrohydrodynamics, or you can say electrochemical deposition. Such type of technology and such different type of synthetic methods also will vary the efficiency of a solar cell. Okay, so here are few of the examples uh, which incorporated the nanomaterials with the solar cells. So the very first one is by Park et al. So you can read that article uh, in Journal Material Chemistry A. So here, if you look what they have done, they have synthesized a thin layer polymer solar cell by use of silver nanowire. So here, how silver nanowire has played a role. So silver nanowires here are being used as a electrode. So instead of the glass and ITO, it has been replaced by the silver nanowires, and hence it clearly proves, looking into the efficiency of the three cells. The first one, if you look, this blue one, that is ITO with the glass, the power consumption efficiency is found to be 5.78%. But when they replaced it, this ITO glass, by silver nanowire with PET, that is the other layer on glass being replaced by PET, the efficiency dropped down to 3.7%. But when the silver nanowires are being replaced by the glass surface, so the efficiency again is almost similar to that of the ITO with the glass, and this indium tin oxide electrode is replaced here with the silver nanowires. So how this efficiency has been achieved? This efficiency has been achieved by this EHD method, that is the electrohydrodynamic spraying of the silver nanowires that was synthesized uh, and then later were deposited as a electrode, and it served as a very good alternative to the ITO electrode. So one of example where nano material can be used into the solar cells. Here, if you look, the two ingredients, one is the polymer and the other one is the C61. That is, it is an example of a organic polymer solar cell. Okay, coming to the second example, where this article highlighted the use of the nanorods. Here in this case, the nanorods of cadmium telluride has been used. So looking into the same images, you can see the vertical alignment, the top view. These CDT nanorods are vertically aligned, and which enhances the transportation of the charges effectively when in the absence of such nanorods. So if you look into the graph for the air mass 1.5, here current and the applied voltage, the first graph which is showing the lower efficiencies uh, is coming from the P3OT, poly 3-oxythiophene polymer only, but when it has been incorporated with the nanorods. Okay, so in this case, it takes a shape of a structured IV curve, giving a fill factor of approximately 50%. You can say VOC zero point 0.7 and JSC 3.12 milliampere per centimeter square. And although the efficiency is found to be only 1%, but in comparison to the cell that has been efficiencies was found only for the P3OT, it was negligible, almost negligible. So what is the role of the nano rods being used here? So as you can clearly see from the data, it gives us the improved optical absorption, right? And this could be arising from the effective dissociation of the excitons. And the third point is the alignment. Okay, see these nano rods are highly aligned in nature. They are vertically aligned, and uh, they provide us the plane for the effective transportation. So electron transport is perpendicular to the plane of the film, which reduces the recombination part here. Okay, so this is one of our example where these the long nanorods are being used as an attractive tool to obtain a better efficiency when compared to a cell without the nanomaterials. Coming to the third example, in this case again the nanorods of CDS has been used and which are being produced by the ECD method, that is electrochemical deposition method. And these nanorods has again effectively increased the efficiency of the solar cell. You can see from the IV curve that is being depicted for all the three condition. One is for the polymer where in the presence of light, and the second one is with the composite and nanorod in the light, and the third one is without the composite and nanorod in the light, and the third one is less, but in light the efficiency it has given a proper IV curve. So looking into the UV visible spectrometer graph, IV visible sorry, absorption UV visible graph. If we look into the absorption band, CDS nanorod, it has been showing a very like a distinguished band at approximately 450 nanometer. And the material that has been used here, that is the polymethoxy ethyl vinylene vinylene PPV polymer is being used. It has a, broader peak at ranging to 500 with a lower efficiency. But when both the two are clubbed and given a composite for the active layer, the absorption rises significantly to 2x times. So this clearly indicates the effective role and the electron transport properties of the nanomaterial in the solar cells. So if you look into the structure for here, the electrodes here are, one is titanium, the other one is gold, and here we are having the these lines, these vertical lines are for the nano material, that are the nanorods, and the background it is for the polymer. So composite is being used, so both of two complement each other and resulting into the effective transfer of the electrons. Okay, I hope here also nanorod, the function of the nanorods as the efficient path for the electron transport can be clearly visible and understood by the SAM images, by the UV visible spectrophotometer graph, and by the IV curve. So coming to the conclusion part, So all in all, we can say that every problem has a solution, right? And how nanotechnology has incorporated with the optoelectronics and given us the uh, uh, better efficiencies when compared to the solar cells without the nanotechnology. It reduces the manufacturing cost particularly. And the second one is the efficiency increases. We have seen through the examples also, the efficiencies increases as the absorption efficiency of the light increases. And this was with the help of the making a thin film of the solar these nanomaterials on either as a replacement to the ITO, that is the electrode, or with the blend composite with the organic part. So the overall radiation to electricity, it helps in the overall increase in the efficiency of cell. The third one is, although we throughout the slides I said that it is difficult, and it is next technology, or you can say the fifth generation solar cells need to be introduced to meet up the percentage, that is a 40% of the efficiency given by the silicon solar cells. Although that has not been yet achieved by the nanomaterials, but again the low cost manufacturing and easy tunability and the alternate to the toxic, or you can say to the costlier material, is a better option for nanomaterials. Third one is the solar cells. These are the promising next generation cells, and but it cannot compete in terms of the efficiency with the general traditional solar panels that are like, I guess most of the houses are having the silicon amorphous solar cells, and institutions also. Those, it will definitely take some decades to replace those silicon inorganic cells with these organic flexible cells, which can be easily applied on either on the surface of the window or on the top of a vehicle, anywhere it can be used. So the practical application of the solar cell, it is crucially important to simplify the fabrication process and to reduce the cost of one dimensional fabrication and the reduction of the one dimensional nanomaterial. And the last one is portable and flexible solar cells. As I said a few seconds ago, these flexible solar cells have attracted increasing attentions and are the coming out to be the booming area of research in case of portable and wearable electronic products. So introduction of nano field into the solar cell is a booming technology, and we can, looking into the general structure and the role of one of a part in the solar cell, we can replace with you can say nanomaterial, which is not only based on the of the inorganic material. It can be the biomass also, it could be chemically synthesized, it could be lab synthesized, or it is a renewable part. Okay, so that nanomaterial, nanotechnology is a vast field. So any type of nanomaterial, nowadays combustion materials are being synthesized by combustion method. Number of hundreds of research papers are there on combustion technology. These such type of materials can also be incorporated with the uh, this optoelectronics. So that was from my side. For I would like to thank my institute, Ganga Institute, for providing me an opportunity, and obviously convener and co-convener Dr. K. Sarojini ma'am and Dr. A. Jayanti for providing me an opportunity. And my special thanks goes to Dr. Dinesh Babu sir for reaching me out, for delivering me a lecture on this 1 week FDP program. So if any suggestion or queries, you can drop me at my email ID. And thank you so much.
Thank you, ma'am, for delivering such a informative and insightful lecture today. Actually, you have covered from basic to advanced level. The way you presented all the even the complex ideas with such clarity and depth, with flowcharts and also animated videos, was truly inspiring. We greatly appreciate, ma'am, for you spent your time and effort, and you have taken and prepared to deliver this such an informative session. Thank you so much, ma'am.
Thank you, ma'am.
Thank
Thank
you,
you
ma'am.
so much for inviting me and giving me an opportunity for sharing my ideas with all the participants. And a big thanks to all the participants for such a good listeners. And if anyone has any query, you may ask, or you can later message me also on my Gmail ID.
Ma'am, some questions are in the chat box, ma'am.
Okay, I will just look into it. Yeah.
Actually, one question is when we reduce the band cap, efficiency will increase. But when we reduce the band cap, open source voltage also decreases. Then how can we tell efficiency will increase? One participant is asked like that.
Yes, actually, this is the main thing to be considered while choosing a material, because if we increase one thing, the other factor decreases parallelly. So, how can we reduce the band gap? We can reduce by changing the, you can say, HOMO and the LUMOS, and that can only be done by introducing some functional groups either on the donor or on the acceptor part. Okay, in that case, the band gap will reduce, but parallelly, VOC will also be decreasing. So that's why the role of the nanomaterial plays a crucial platform here, because in that case, the nanomaterial can easily be tuned depending upon the availability of the size, whether the nanometer is a 5 nanometer or 10 or 100 nanometer you can take. It will not we can say it will not change the band gap, but it will increase the VOC, or it will make the constant VOC as compared to the previous one. Okay, so that can be done by considering into both the two or three factors, JSC, VOC, and again the band gap, by tuning the use of the nanomaterials. You can further find out by reading some few articles on the nanotechnology, how these materials can be used in the solar cells for maintaining the VOC values.
Okay, ma'am. Thank you. Ma'am, I am having one question, ma'am.
Okay.
In your work, you have calculated HOMO-LUMO values. They are experimental values or theoretically calculated, ma'am?
Yes, ma'am. These values are calculated theoretically by Gauss view, by Gaussian software, and by B3LYP method. So all these experimental values can be easily find out. Uh, you can also see where the molecule will be absorbing exactly by putting into the molecule structure. It will give you all the details for the UV visible and spectra, and for the band gaps also, from the like highest where the last means band will be observed, that will be considered as the HOMO, that is highest occupied MO molecular orbital, and the next to it will be the LUMO one. And from both the two, you can just subtract the values of both the two energies with reference to the vacuum level. That will give you the values. HOMO and the LUMOS, they are being calculated theoretically.
So you did both experimentally and theoretically, yeah, ma'am, in your work, your research work.
Yes, yes, ma'am. Yes, ma'am.
You have done both.
But
You
using
have done
using
both.
Gaussian using DFT calculation and Gaussian, we can find out the HOMO and the LUMO values exactly. Yeah.
Okay, ma'am. Thank you so much, ma'am. Really, I hope everyone is benefited in this session. Even the beginner to advanced research level, all are benefited. Thank you so much, ma'am. Thank you once again.